Looks good. Thank you. Okay. We're waiting for a minute. Good.
Good. Alright, do you want to start?
Sure. So, hello everyone. So, welcome to the first part of the machine learning series that we're going to run. Today we're going to cover KNN and support vector machine. And the second part will be about clustering algorithm. So, if anyone take your time to put in the sign in. There's also the link to the slide in there also. Let's give everyone 1-2 minutes for that. Good. Okay. So this presentation will be covered by me, Dui, and Darcy over here, and later on Zach. And so firstly, I want to talk about the definition of machine learning. So the term machine learning has been thrown around a lot these days, and like everywhere you see startup throwing machine learning on their portfolio. And so the idea about machine learning has been there for a long time, but with the resurgence of deep learning algorithm, traditional machine learning has been a bit hidden behind the shadow of deep learning. And so machine learning is the broad category, but also in there is what we call now traditional machine learning algorithm. For example, what we're going to cover today, which are K-nearest neighbor, KNN, and support vector machine. So these algorithms are not neural network, and take a different approach to do machine learning, and it offers an alternative to the data and computational hungry neural network that you see running by Facebook, Google, Uber, etc. And also, using these algorithms, we can have a more interpretable model of our data, which are a goal of many deep learning algorithms. And so, the first one I want to talk about today is K-nearest neighbor. So what is K-nearest neighbor? So K-nearest neighbor, the idea, the intuition behind K-nearest neighbor is quite simple. It's a classifier that classifies based on the value, the data point around the data point to be classified. So actually, let's get a picture on. So for example, I want to classify this green circle right here. And so what K-nearest neighbor would do is take vote from the neighboring point of that data point. So in this case, for the first circle, for example, if I choose k equal 3, I'm looking at 3 nearest neighbor to this data point. So the 3 nearest neighbor would be the 2 red triangle and the blue square right there. And so each of the neighbor would have a vote on the classification of this new data point. And in this example, if we have k equal 3, 2 out of the 3 vote is red triangle. So in this case, we will classify this data point as red triangle. However, if we expand the search to be k equal 5, so we're looking at 5 nearest neighbor, then there are 3 neighbors who are blue square, which causing the classification to be blue square. And so the central tuning that you can do for k nearest neighbor algorithm is to choose your k, the number of neighbors that you're going to consider. And so I have been talking about nearest neighbor, but what really is nearest neighbor? So we want to measure how close 2 data points in a vector space, right? So there are many different measuring technique, like basically different metric that we can use. So for example, the Minkowski, I don't know if I pronounce his name right, sorry. The Minkowski are the families of different metric that you can use which parameterize on P. And so there's 2 special one that we regularly use, which is the Manhattan distance, which are Minkowski when P equal 1, and Euclidean, which are Minkowski when P equal 2. And so these are basically way to measure how close or how far to vector is, and basically gauge the similarity. So basically, you plug in all of the neighbor, then you get the list of all of the nearest neighbor. Then you can use that to get the vote. And so Euclidean is, if anyone familiar, is basically just Pythagorean theorem. On the other side, there is also cosine similarity. So cosine similarity is, rather than measuring the magnitude of the similarity of the vector, we're looking at the angle in which 2 vector is making with each other. And so that's another way to look at the vector similarity but disregarding the magnitude of the vector. And so back to choosing k. So as we can see that choosing different number for k has an impact on our result for our model. For example, if you choose a really small k, so there's a better illustration for this. So for example, this is a toy example that I adapted that look at different amount of k and the effect of it that it has on the decision boundary. So as you can see, for example, when k is 1, basically your model is just overfit onto whatever the training data it has, and so you get a very ragged decision boundary. And as k increase, you get a smoother and smoother separation between different class. So in here there's 3 class. This is one of the scikit-learn example. In here they are looking at the iris dataset, which this is the first 2 feature of the iris dataset. But so as k equal 15, you begin to get a relatively decent separation, and when you increase this all the way up, you begin to get a very smooth and very straight decision boundary, class separation. However, you lose all of the outlier in various places. And so, in summary, KNN is an intuitive and simple to understand model that doesn't require training beforehand, but and because of that, it's easy to build an online classifier. You could just keep putting more new data point, and the model can essentially adapt to your new data flow, data streaming in. However, as data point increase, well, that's weird. So as data point, as the number of your data point increase, the number of data point you have to compare every time you do the classification also increase, and thus you increase the computational cost. And so it is fast for a small amount of data, but it gets gradually slower over time. Also, as you can see, it's very sensitive to outlier, especially if your K is really small, and it's very sensitive to unbalanced data set. And next we'll have, well, first, any question? Okay.
Okay, so the next thing we're going to explain is support vector machines, which is our other model. But first, I'm just going to briefly go over what linear classification is, so you sort of need to know that as well. So there's an important distinction between linear classification and linear regression. So what linear classification does is it takes in some training example and then classifies it into a discrete number of classes. So for example, you could have a picture and you need to say, oh, is this a dog or is this a cat? So that contrasts with linear regression, because with linear regression, you take in some data point like the width and length of flower petals, or not the or something, and then what you need to do is you need to sort of classify it on a continuous scale, right? So, for example, if you have different characteristics about a house, like the amount of square feet, the amount of bedrooms, you want to figure out the price of that house. So it's not saying like this house is one of a discrete set of classes. It's just sort of trying to predict some continuous output for the training example, whichever you're using. Oh, yeah.
Does that mean that linear regression is more quantitative and classification more qualitative? Always?
In a way. They're kind of closely related, but the main difference is, so you'll sort of see, I'm about to go into sort of the internals of classification, but sort of the main difference is at the end where you, instead of keeping some final score, you instead interpret that as the likelihood of something being in a certain class. So it might make sense after a few slides, but if it doesn't, ask. Okay. So linear classification is sort of part of this general training process. So in order to linearly classify something, you need to go through a few steps. So first you need to have some input training data in order to train your linear classification model. Then you need to make predictions based off of your model, and that's the main linear classification equation. So if you know linear algebra, you know that that's a matrix multiplication. So you basically take a vector xi, which represents your training example, multiply it by a weight matrix W, and add a bias. So it's a pretty simple linear equation, and that's why this is linear classification. And then after that, you also have to compute the loss and update the model, and I'll get into that later. So, for example, say we have this image of a cat, and we need to classify it as being either a cat, a dog, or a ship. So we see our parameters from before, right? That we have a parameter W and we have a parameter B. So in order to classify our input image, we first stretch it out into a simple column vector, and each entry in that vector is a different feature. So in this example, it would just be the different pixel values, but it could really be anything you decide based on what information you want to classify. So then you multiply that with your weight matrix. And so how you do matrix multiplication is you take one row and you dot multiply with this column to get one score for each of the rows. So for multiplying this row with the input vector, we get this score. The second row, we get this score. And the third row, we get this score. So basically, each row of weights corresponds to getting a score that the input vector will be in a certain class. So the top score is the score that this image is going to be cat. the second entry in the answer is going to be the score that it's a dog, and then the third is the score for ship. So for linear classification, we just take the maximum of all of those scores. So for this example, we see the largest score is the dog score, so we would incorrectly classify this as a dog. So, sorry, going back to your question, if this were just linear regression, then we would sort of keep that output vector just as it is, as continuous values.
And
So-
output that number.
Yeah, so like we would, so it doesn't really make sense to do it for a cat, but we just sort of keep the output, and we wouldn't instead say, oh, it's in a discrete class. But you'd still use this general equation, and you would update the weights with that.
So instead of having in like cat dog ship, would this be more quantitative values?
Right.
So it would be like number of something.
Okay. So now we can actually get into what the support vector machine does. So support vector machine, and for our examples, a multi-class support vector machine as opposed to just having two classes, so you can have lots of classes. It's essentially a loss function. So once we do linear classification and we get our class scores, and then we use those to classify our object, they might be wrong, right? So in the last example, it incorrectly classified the picture of a cat as a dog. So that's wrong, and we want to quantify how wrong that is so we can update the model parameters. So basically, what this long equation does, which we'll parse through in a moment, really quantifies how wrong our models were, and it also sort of informs how to update the model so that it's less wrong, and then we have more accurate predictions. So basically, what this loss function for the SVM is creating is basically a model that creates a boundary between two different classes of points. So we'll see this in a minute, but all of the red points are pretty much on one side of the boundary, and then all of the blue points are pretty much on the other side. So if you have, and then there are also these dashed lines, and that represents you have a certain margin that you want to say, like if this point is within this margin, then I want this line to be a little bit further from that. Right, so if the line was like this, we would have much more red points in sort of this marginal area or past it, and then we use those to inform our model and sort of push the boundary back right into the middle. So this is the loss function. So for this is just the loss function for one example. So for one input vector, you would take the sum of all of the classes except the correct class of the example. So if, for example, we had a cat, we would do this for the sum of the scores of all of the classes that aren't cat. So we would sum it up over the dog score, the ship score, whatever other classes that aren't a cat you have. And then the actual loss is the maximum of 0 and the score for class J, which is the incorrect class, and then minus the score of the correct class, and then plus some margin of delta. So this loss will be large if the score for an incorrect class is much higher than the score for a correct class. So in this graph here, we say the x-axis is the score for an incorrect class, and then the y-axis is the loss. Then we see that the loss is very high if the score for the incorrect class is not less than the score for the correct class by a certain margin delta. So this inflection point right here, that's where the incorrect class is exactly the correct class score minus delta. So you can sort of see that more intuitively with this graph. So say we did classification, and then we got these scores for each of a few different classes. We know that the cat score is the correct score. And so we want to ensure that the correct score is much higher than all of the incorrect scores. So basically, if an incorrect score, say the dog score, is not a certain margin below the correct score, then it contributes to the loss. So in this example, the dog score, the horse score, and the bird score would all contribute to the positive loss. Does that make sense so far?
Yeah, about the delta, like how does that come in?
Okay, so just pretend we didn't have delta. Like So pretend that all this did was just do the difference between the incorrect score and the correct score. Then if the incorrect score was just like 0.0001% smaller than the correct score, then that wouldn't contribute to any loss. But we don't really want that because we want the correct score to be much, much higher than all of the incorrect scores, because then our model is going to be correct more of the time, right? So we want to say the correct score has to be this certain margin delta higher than the incorrect score. Right, so like in this previous example, if delta were 0, this example wouldn't have any loss. But since delta is positive, we have a loss for the dog function and all of those, so then that informs how we update our model. Yeah?
So in practice, is delta just fine-tunable? Like you just take the best delta out of it?
Yeah, so delta is a hyperparameter, so you sort of have to, for now, manually fine-tune it and see what works best. Okay, so then we can, over all of our training examples, calculate a total loss. So this is mostly just used to see, at this moment, how well your model is doing. So the total loss is just the average of the loss for each of the training examples. So that one's pretty simple. And then, once we have our loss, since, remember, the loss is sort of a measurement of how badly our model is doing, we can use the loss to inform how to update our model. So if we know how to decrease the loss, that in turn will make our model better. So in order to do this, we use gradient descent. So we take the derivative of the loss and then update the weights according to that. So basically, if our dog is contributing positively to loss, then we need to decrease the weights that made that dog score high, is basically what the derivative is doing. So, and by the way, this 1 right here means if this value is not positive, then just ignore it, is basically what that means. So you can sort of read these. I'm not going to derive them in the presentation, but if you have any questions, like if it's not intuitive, does everyone sort of understand? So, okay. So some of the pros and cons of using a support vector machine is, so a pro is that it's pretty quick to classify an example, because remember, for k-nearest neighbor, you had to compare one example to all of the other training examples, whereas in a support vector machine, you just have to do a simple matrix multiplication. And so SVM is also pretty easy to implement, especially compared to a lot of larger machine learning and maybe deep learning examples. Some of the cons are that training is pretty slow, so you have to sort of iteratively make your model better over your training data, whereas in KNN, all you had to do was memorize the data and then your model was trained. And another con is that support vector machines, they can't really like quantify some of the more like subtle relationships between different variables. So, for example, some different types of models, for example, a convolutional neural network or a deep neural network would have done better classifying an image. So a simple support vector machine can't really figure out some of the more sort of the higher level relationships between each of the different entries in one training example.
But KNN can?
So KNN not really either, because all it does is it sort of says, are these two instances of a training example similar? Whereas if you were to do something like I don't know, say a convolutional neural network, two images could be very, very different, but they could still ultimately belong in the same class. So a KNN wouldn't really be able to classify that well.
So to help you visualize that, let's say you're trying to use KNN to pick an image from like a database or something. You might be trying to find a whale and just give you like a blue Pepsi can, just because the pixels are like close to that space. You can't really tell the difference between images.
Okay, so any questions? Okay, so then we also have upcoming events. Yeah, come to these. So we have a weekly society and machine intelligence discussion. That is next Wednesday, and then we have a paper discussion next Tuesday. And then, okay, so we have some example code for you to go over. And Zach, do you want to go over this? Okay.
Now, you guys can open up your laptop and try to go through these different Jupyter notebooks. I think you can comment even though you're not allowed to edit. So you can just make a copy of
You
them.
want me to switch on?
I'm good. I can use yours.
Yeah.
Oh yeah, actually use mine.
Yeah. You want to use it? Yeah, sure.
Let's remember.
On this other side. Oh, it's streaming?
Well, it's fine.
Oh, it's fine. You can keep streaming. It's fine. Oh wait,
No,
the screen would be
off.
off. Oh no.
Okay.
Oh my gosh. Wait. Oh. Okay, let's just use this one. Let's just use this one. I don't want to stop the
Okay.
streaming.
Okay.
Yeah.
I don't know. You can just plug it in there.
Make sure it's on the screen. So open OBS. Extend.
Yeah, because like,
Yeah.
can I pause screen?
You can just add a new one.
What's going on?
Display.
As long as your loss is decreasing, that means
Yeah.
it's
Go.
So the actual number of the loss.
Okay.
There you go.
And just go. There you go.
Thank you. So yeah. Good evening, guys. Just a bit about myself. My name is Zach, and I'm a sophomore at Boston University. I have been involved in the field of machine learning for quite some time. Last summer, I worked in a major investment bank in China, basically doing natural language processing, different machine learning projects, including predicting news sentiments, and use that to help us invest in securities. And we here, BUMSC has also done a lot of great projects. As a matter of fact, several weeks ago, we won first place at a hackathon hosted by Google at MIT. So this is a great club, and I learned so much from the guys here. So I would encourage you to stick with us, and I'm sure you will advance dramatically. So basically, today, today we're going to give you two code exercises, one of which is KNN. I have already commented the code, so it should be super self-explanatory. And I also deleted some code, so you can go to the scaffolded KNN exercise and try to implement the algorithm yourself. Of course, after I finish maybe talking about this SVM example. So you should have plenty of time to do those. Great. Feel free to ask any questions, even though I don't really use SVM. You guys should definitely come to the deep learning lectures held by Curtis and others in the coming weeks. Those will be really helpful.
Can you go back to the links real quick?
Oh yeah, sorry about it. Basically, just bit.ly and then complete something example. On the SVM is 2. Mm-hmm.
Also, the link to the presentation slides is in the sign-in sheet.
Is everyone good? Alright. So yeah. So for the SVM, see if I can enlarge it a little bit. Basically, Darcy has talked about classification, and just to maximize your learning experience here today, I'm gonna talk about how to use SVM to do regression. it has really similar ideas, so I'm sure you should be able to follow along. And even if you don't understand the classification, this regression, I believe, is actually simpler. So we're going to be using TensorFlow, which is basically like this industrial-ready machine learning package or library that most professionals prefer. So this is a great place to get started. So I'm gonna skip over these import steps. Basically in TensorFlow, what it does is basically it would create a bunch of computational graphs first, and then in the graph, it basically like every single branch you can imagine as some kind of a tree. Every branch would be some computational step, such as like ax plus b, a matrix multiply x would be one step, and then this thing plus b would be another step. Yeah.
So just to clarify, all the operations are like nodes.
Right. Yeah. I'm trying to keep it like kind of in layman language. So yeah. Basically, in doing so, TensorFlow can do parallel processing and computation. This really comes in handy when you have like a lot of data you want to compute at the same time, and you also happen to have maybe different GPUs. So the data set we're going to be looking at today is called the Iris data set. When you're loading a data set from TensorFlow, what you usually can do is just to do this import function. Then you should be able to take a look at what it does by doing this describe. Okay, not very used to this keyboard. And also, one good thing about Google Colab is that it provides free TPU support. So TPU is like some kind of like a GPU that is optimized for machine learning.
Also, it includes a GPU as well. So
yeah, pretty sure.
if you
I made a typo or something.
Machine learning projects, it's definitely a great place to start since it has TensorFlow installed already and all your necessary libraries.
So it's Python. What else Python?
It does. Oh, nice.
It's from scikit-learn, right?
Anyway, so yeah, I mean, by running that function, I don't remember the exact name of that function. You should be able to get what this data set contains. So basically, we want our training data to be the. Let's see. I think we have a comment above. Sepal length, and then we want to use sepal length to predict the petal width. So sepal and petal are basically like two different parts from I think a kind of flower called iris. And then basically like these two, you would imagine them to be correlated, right? If they are like these two parts from the same kind of flower, if one is large, then maybe another is also large. Or maybe they have some like more complex relationships. So we can use SVM to help us detect it. Then here we are basically just generating random indices, and then after we get indices, we can just use this very interesting Pythonic expression to get the test indices. Basically, like what is not chain indices are just test indices, and then we split up our data, and then basically, like we have to have some test data so that we know how a model is doing after training with the training data, right? And then batch size is basically just to specify like how many rows or how many like number of examples you want to train at the same time. And then for TensorFlow, as I have said, we have to construct nodes in the graph. So basically, we just specify, okay, so for the training data, we want this to be maybe something like basically like TensorFlow has this thing called placeholder. Usually like people use this to place training data. It has a lot of advantages, but I won't go into them today. But I think it's pretty easy to follow them if you go online and find some tutorials. basically like for training data with placeholder, and then for the weights, the parameters or variables we have to learn, we use this class called a variable. And because it's a class, not a method, so it's in uppercase. So basically, this is just a very simple regression model. It just literally is just like ax plus b. So in TensorFlow, you do the multiplication and then you do the addition together. You don't like write them out directly, because right now you're doing the construction phase. And then this is the core part. We're declaring the loss function. And then for regression, right? Basically, we just want to make sure like the target value minus the prediction is close enough. So basically, like, these two values are close enough. So we can just take the absolute value. And then, as Darcy has explained, we can use some kind of delta value. In this example, it's called epsilon, but it has a very similar idea. Basically, we want the difference to be larger than epsilon. If it's not, then yeah. So in this case, epsilon has a value of 0.5, and then we got a loss. And then we just specify linear weight, and then we use gradient descent, as Darcy has talked about, to do the optimization. The good part about TensorFlow is like after you have defined the loss function, you will take care in minimizing it for you. So you don't have to calculate its derivative and then try to find its minimal value by using calculus or whatever. TensorFlow has a feature called auto differentiation, I believe. It might be something called backward differentiation, but basically like it uses the graph you have constructed to minimize the loss function. I will give you some resources to read after I finish this presentation. And if you're interested, you can learn more about how TensorFlow does it under the hood. So basically, this is just standard training process. We load the training data and test data into this basically placeholders, and then we train. And then for every 50 iterations, we print out the current loss. So yeah, as you can see, the SVM does generalize pretty well in regressing their relationship, and the loss looks pretty nice as it keeps decreasing, and then it stops. Actually, 200 is more like, I think, a value that is picked after like training it for many times. So you won't know like you have to train like 200 times to begin with. Usually it takes a lot of trials and errors. The fun part. So yeah. Any questions? I mean, you may not have completely understand it. That's okay, because that's usually how I felt last year when I was here listening to the lectures. So what I would recommend is for you to try to do a lot of independent reading back at home. The book that I have used a lot is this book called Hands-on Machine Learning with Scikit-learn and TensorFlow. I believe after today, you should be pretty comfortable in diving into chapter 5. So after you have some time, maybe this weekend, you should definitely try to read through this chapter. It's super helpful in reinforcing your understanding of SVM. I think it also talks about KGG somewhere. Somewhere I think prior to that. But yeah. So the rest of the time would be yours to try to maybe implement this KGG algorithm. If you have difficulties, you can either ask one of the BUMSC members, or you could just, if you want, you could take a look at this complete KGG and then see if you have got the algorithm right or not. So yeah, thank you very much and happy coding.
So in the SVM, yeah, we have one weight, one bias. Are you able to like increase that? Was that bias? So yes.
Hey guys, I want to just take the time to introduce ourselves. I'm Julius. I'm currently co-president of MSC. That's Devin. He's also an president.
Also one. Yes.
Go around the room.
I'm Zuri. I'm one of the exec member of the
Hi, I'm Darcy, and I'm also on the board.
I'm Darren, also on the board as well.
Curtis, keyboard.
Yeah, I'm also on the board. Yeah. If we could like get your name and major, maybe your Richard and a junior.
Yes.
Nice.
There's two of them, Richard.
That's
why I'm in physics.
Cool. Ian, undecided.
Awesome. You will start noise. Hey everyone, I'm Keshav, and I'm double majoring in physics and CS.
I'm Smegda. I'm majoring in computer science and freshman.
I'm Gonzalo. I'm a PhD candidate in Spanish literature, but I just wanted to say this because I have some programming background. So.
I'm Jacob. I'm a freshman in CS.
Awesome. Thanks, guys.
Yeah, thanks for coming. Feel free to keep contact with us on the
There's also pizza left if you want some.